All right, so welcome to a new video on covering spaces. So in this one, we're going to explain how to construct, how to construct them really in a systematic way. And I think the best way to approach this is sort of to revisit our favorite example, and we'll explain a way of thinking about it that will be easy to generalize for other covering spaces. Our goal being, well, how do we construct a covering space that is simply connected, just like in this case, right? Like R is simply connected and it covers this one. All right, so the way I want to think about R is as follows. So this is right, like, so this is basically going back to the beginning of the course. This is like the way we've been thinking about it for a while, hopefully. So for every real number t in R, I want to think about it as like the path in S1 that starts at the complex number 1 and it turns around making 2 pi t radians in total. Okay, moving at constant speed. Um, right. So the way to explicitly write this, of course, is I take the number t and to it I assign to it the path that to s it assigns e to the 2 pi sti. And of course, when s is 0, this is just 1. And when s is 1, this is e to the 2 pi ti, right, as we want. Of course, let me recall this for you. So the final point, of course, it doesn't depend on t up to an integer shift, right? If I have t and I have t plus 1, then then the final point, it's, well, e to the 2 pi I t or e to the 2 pi I t plus 1. And of course, the ending point is the same. But the way in which we got there, it's different. So really, these paths are distinct, right? Like this one loops once more. And this is what we distinguish, right? Like the idea in which we used to unwrap S1 is to exactly, well, keep track of how much we're looping around it. So let's see, what have we gained? What is happening here? So what is happening on one side is that here I have R, that is a simply connected space. And now I'm thinking of it as a collection of classes of paths in S1, right? And that is what we will generalize later, somehow for other covering spaces. The simply connected covering space of that we build will be built as a collection of classes of paths. But what is this collection? So this collection we've seen, of course, before. These are like, so these classes of paths we're taking here, they're like the classes of paths that start at 1. So as such, this is like it's a piece of the fundamental groupoid of S1, and it's the piece that corresponds to the pre-image of 1 by the source, right? Because this is exactly what it is. These are like the paths, well, the classes of paths that start at 1. So what we've done also is like we've taken a piece of the fundamental groupoid and we've given it the structure of a topological space. We called it the fundamental groupoid. As we defined it, was just like a set with some operations, but now we see that a piece of it at least is a topological space. And this is the game we're gonna pursue in this lecture. So on the one hand, we're gonna provide a topology in the fundamental groupoid. And this is sort of interesting by itself. And additionally, then what we will observe is that the source fiber of any point, in fact, is a good model for like a simply connected covering space of the base, right? So that's exactly what we will do. So let me move on towards the definition. So indeed, what's my goal? So I'm gonna be given a topological space X, and I will have to require that this topological space is reasonable enough. I will explain in a minute what that means. And given such an X, what we will do is we will construct a simply connected covering space of it called X tilde. And such a covering space will be called the universal cover. And the reason why it's called the universal cover is, well, first of all, it will be in fact unique. So we will provide one particular recipe for constructing it, but it will turn out that any other covering space that is simply connected will be isomorphic to it. So okay. And the other reason why it's called universal is that every other covering space of X will be built out of, well, not every other, but let's say every path connected covering space of X will be built as a quotient of this X tilde, the universal cover. So X tilde sort of knows everything about all the path connected covering spaces of X. And as I said, this X tilde will be built as a source fiber of the fundamental groupoid with its natural topology that we will introduce in a second. All right, so we said that there's a natural topology. No, sorry. We said that we need X to satisfy a certain. We need X to be reasonable enough. And what should this mean? So as we've said, we want X tilde to be simply connected. And now we recall that, right, due to the covering map, X tilde and X are of course homeomorphic locally, at least, right? So that means that, for instance, like if I want X tilde to be simply connected, it is quite reasonable that I require it to be locally simply connected. And if I require X tilde to be locally simply connected, then because they are like locally homeomorphic, I should require X itself to be locally simply connected. So this is an assumption that I will be assuming all throughout the discussion, and sometimes I will just not say it because I'm assuming it. And I mean, a fact that is interesting is that you can do, yeah, washing machine. We can do a bit better than this. So if you read Hatcher, you'll see that the assumption that Hatcher puts in X is that X is locally semi-locally simply connected, which is slightly weaker, so it's a bit more general. But I don't want to. Well, I mean, I don't want to deal with pathological stuff. And for instance, you may check that CW complexes, of course, are locally simply connected, and so on. So for our purposes, let's say that this generality is enough. All right, so let's get to it. Let's define a topology in the fundamental groupoid. So, well, here's the definition. But before I get to the definition, I think it's good to try to give you an idea of what this topology should be. So let me show you a picture first. All right, so what is the intuitive idea? So the fundamental groupoid, right, it's a set of homotopy classes of paths relative endpoints. So if you give me a gamma, which is a path, and you give me its class in the fundamental groupoid, what I'm asking myself is, well, what is the natural topology here? What does it mean for another class to be close to the class of gamma? And at least intuitively, and in fact, we did introduce this in one of the problem sheets as an optional exercise or something like this, if some of you did it. It's like, well, then the natural topology in the fundamental groupoid is basically the following. So just take a path, then we can say that another path is close to it if they're like point-wise close to one another. That defines a topology in the space of all paths in X. And now the fundamental groupoid is a quotient of the space of all paths, right? Because these are equivalent classes of paths. And sort of then the fundamental groupoid just has like the quotient topology. All right. The thing with this though is that, I mean, we can do a bit better, and instead of doing it in this sort of abstract way of defining it in a big space of all paths and then quotienting, which is like a really big quotient, right? Because this space is like super big, the space of all maps, of all paths. Then we can be a bit more explicit and try to define it the same topology directly in the fundamental groupoid. So what is the idea? So the idea is like, how do we formalize that a class gamma is close to another class? And at least there's something clear that we can do, which is that we can take, for instance, like a tiny ball around the initial point of gamma. We can take a tiny ball around the final point of gamma. I call this Vs for source and Vt for target. And now what I can do is, well, okay, then a path that is very close to gamma is basically a path that sort of, it's a concatenation of a tiny path that goes from Q, a point in Vs, to gamma 0, then it does gamma, and then a tiny path that goes from gamma 1 to P inside of Vt. So for different choices of Q and P, all of these are like, they represent different classes in the fundamental groupoid, and sort of this should define sort of a neighborhood of gamma determined by, well, of the class of gamma determined by Vs and Vt. Okay. All right, so let me write the proper definition. Basically, I'm gonna say the same I just said, to be honest. So we say that the topology in the fundamental groupoid is defined by a basis. The basis is made by these opens that are indexed by Vs, Vt, and gamma. And basically, indeed, as I said, you should think of this as an open of the class of gamma, sort of given by these opens in X itself. So here gamma is a path. Then Vs is a neighborhood of gamma 0 that I can require, well, that I do require to be simply connected, right? And I can do this because X is locally simply connected, so I can take arbitrarily small neighborhoods with this property. And the same for Vt. Vt is a simply connected neighborhood of the final point. And right, so given these three pieces of data, these three inputs, what is the open? So the open are all the homotopy classes relative endpoints of paths of the following form. So tiny path nu from q to gamma 0. So this is something like this. It's a path that is happening only in Vs. Then concatenated with gamma itself, and then concatenated with nu of gamma 1 to p, also contained in Vt. All right. So these are like all these homotopy classes. So okay, that's the idea, this definition, and now let's prove that this is actually a topology. So the first remark, of course, is that it's here. The two neighborhoods are simply connected, right, by assumption. So that means that the fundamental groupoid of Vs and Vt is the pair groupoid. So that means that for any 2 points that I choose in either side, the paths between them, well, there's only one homotopy class of paths connecting them. What that tells me, right, is that basically the nus I choose here, the particular nus I choose, are irrelevant because there's essentially only one possible class of paths connecting gamma 1 to p, and likewise, there's only one class connecting q to gamma 0. So what this is telling you really is that once you've given me gamma, if you tell me, well, I want to find another path, another class of paths connecting now some q here with some p here, basically I don't have any choice, right? Like all you can do to connect them is connect q in any way, all of them are equivalent with gamma 0, then you do gamma, and then you connect with p with any way you can because all of them are unique. So, okay, we'll see a consequence in a second. Well, let me maybe say the consequence of this first, and then we'll go back to this. So the consequence of this is basically, as I said, that once you've given me Q in Vs and P in Vt, the path that I've chosen connecting them in this U, Vs, Vt, gamma is unique. So that tells me that this open set, it's actually homeomorphic to Vs times Vt, right? So at least locally, I mean, it is not true that, of course, globally the fundamental groupoid is like the pair groupoid, but at least locally they are homeomorphic, right? So basically what I will be saying in a second is that this is a covering space of the pair groupoid. Right, so this is the picture you have in mind. Basically, Vs and Vt tell me and once I know gamma tell me everything. So this sort of maybe clarifies this second statement here, which says, okay, let's suppose I have a neighborhood Vs, Vt, gamma 0, and then I have some other U, the same Vs, the same Vt, but some gamma 1, where gamma 1 belongs to this neighborhood. Then the claim is that these two neighborhoods are the same. And the reason is, well, basically the picture I did it here, hopefully you can understand. So let's say you have gamma. I mean, okay, I guess like this would be gamma 0 in this example. And let's say gamma 1 is like gamma joined with this maybe blue line. Then to parameterize the path that goes from gamma to p prime, it doesn't matter if I do red path, gamma, the dotted green path, or if I do red path, gamma prime, and then the solid green path, right? Of course, they are homotopic because whatever I've added from to gamma to obtain gamma prime, which is the blue part, well, when I add this, it will become homotopic to the other green segment, right? So basically what I'm saying is that, I mean, once you've given me gamma and Vs and Vt, gamma itself again is not important because any other path gamma connecting Vs with Vt sort of sufficiently close to gamma will provide the same neighborhoods. So this again supports what I'm saying here, that a neighborhood looks like a neighborhood in the product. And also this sort of claim 2 also almost immediately implies claim 4, which is the following. So if you give me two opens, Vs, Vt, and gamma, intersected with U of Vs prime, Vt prime, gamma prime, and these are disjoint, then, I mean, how does this happen? So this happens basically if you have gamma, you have the two neighborhoods, and then basically gamma prime has to be something that also connects, well, one point here in this neighborhood with another point here in this neighborhood. So basically, the way in which you intersect them is you just intersect the neighborhoods VSs and the VTs among themselves, and then you just to choose as your reference curve some gamma prime prime that connects points in this intersection and is close to gamma and gamma prime. All right, so basically what this is telling you is that the intersection of opens in the fundamental groupoid, it works exactly in the same way as it does in the product of x with x. So again, this says that the topology here is exactly the correct topology for this to be a covering space, which is what we have shown. I invite you to check all the details of this claim, but hopefully, I mean, these are all the main claims that you have to go through. All right. So a corollary. So okay, now we are done. The fundamental groupoid has a nice topology, and it's a covering space of probably the thing you would think it is. But what we're gonna do next is, well, observe that this already gives us a nice corollary, which is the following. So if I have a cube, a point Q in X, and I take the source fiber over it, so the preimage of Q by the source, so these are all the classes of paths that start at Q, then all these paths, I mean, they have like the first point fixed, but the final point is not fixed, so I can project by taking the target to X. Now, this is a topological space, right? Because it's a subspace of the fundamental groupoid. And the claim is that this topological space with the target is in fact a covering space over X. Why is this? So let's look at the topology here. What is the topology here? So the topology here is generated by the following basis, by use indexed by VT and gamma. What is this open? So basically this open is the same open we had before, so indexed by some VS, VT, and gamma. But now because we're intersecting with the source fiber, then we don't have a choice of moving the initial point. So basically we forget about VS, and that's it. So what that tells me is that the source fiber locally, it looks like locally like VT. So it looks locally like X. All right. All right, so this shows that the topology on the source fiber is basically a topology that is compatible with this projection to make this into a covering space. And now what else, what more things we have to check? So for instance, here we have to assume that X is path connected, because otherwise this cannot be a covering space, right? Like if X is not path connected, you won't be able to connect all the points to Q. So then this won't be a covering because some points won't have a preimage. And locally simply connected, we need it for X as well, just because we need it to be able to construct. What am I saying? Well, I mean, this we just need to show in the next step that this covering space I'm constructing here is in fact the universal cover. It's simply connected. So okay, I invite you again to complete the details here. And let's move on to the main statement, I think, of this lecture, which is the following. So this covering space we just constructed, so source fiber, is in fact the universal cover. And now, as you can see here, I'm in fact adding base points. So we're going to be looking at covering spaces that are pointed. And what that means, of course, is that the base point I choose a preferred base point in the covering space that lifts my base point in the base. Now, if I have X and a base point Q, and then, well, I mean, what is the reasonable thing? So then for the universal cover, I choose the source fiber over the base point, so S minus 1 of Q. And what do I choose as base point? Well, I choose the canonical path in this class, which in this family of paths, which is of course the constant loop at Q. Okay, so this Q tilde is a constant path or loop. All right, so the claim is that this X tilde Q tilde is the universal cover, and basically that means that we have to prove two things. One, we have to prove that it's simply connected, and we have to prove that, well, in fact, that it's unique up to homeomorphism. So every simply connected covering will be, in fact, isomorphic to this in a precise sense that I will explain later. All right, so let's look at the proof of the first claim. Why is this simply connected? And we should be a bit careful about this because it's a tautological proof in some sense, because out of the way in which we have constructed the universal cover, this property is almost immediate, but it's a bit of a logic kind of argument. So let's see. So what do we have to show? So if you give me any loop beta tilde in the universal cover, what I want to show is that beta tilde is null homotopic, right? I want to prove that the class of beta tilde is the constant class, and if I do that, I'm done, right? Because b tilde is arbitrary, and I will prove that the fundamental group of x tilde q tilde is just trivial. All right, so how do we do this? So the first thing we can do, of course, is we can take this loop upstairs and we can project it downstairs by the covering map, by the target map. And that will give me another loop called beta, that is a loop in the base. Now, the first sort of out of its definition, what we see is that beta tilde must be a lift of beta, right? And this is, well, I mean, sort of, I built beta out of beta tilde by projecting, so it's a lift immediately. So beta tilde is a lift. And also, if you notice, beta tilde is a lift that, by definition, I mean, its initial point and final point, of course, is the constant loop at Q, right, as a point here. Okay. Now, what you can notice is that we can consider another lift, which is what? So given the path, the loop beta, sorry, we can consider another lift, which is the following. It's the lift that to each t, it assigns the class of the path s goes to beta t s. Right, and this is well defined. Why? Because it's a path. It's a path that it starts at q, and as such, it's a class here. So this is a well-defined lift of beta. And what that tells us basically is that these two paths, beta tilde and this, they must be the same. Why? Because they lift the same loop, and they both start at q. And sorry, and they both start at the class of the constant path. They should read class of the constant path. Let me maybe stop for a second and change that in my notes so I upload them correctly to you. 1 second. Right. So these two are the same. And now what can I notice? So beta tilde, it's a loop in this space, and that means that beta tilde of 1 must be q tilde, the base point, which is the class of the constant loop. But at the same time, by this equality here, beta tilde 1, it's 1 of this, which is, well, it's s goes to beta of s, which is just the class of beta itself. So that tells you that the class of beta is the class of the constant loop. So basically, beta is null homotopic, and the null homotopy of beta can be lifted to a null homotopy of beta tilde, right? Just because we have the homotopy lifting property. So that tells you that beta tilde, in fact, well, I mean, it's null homotopic, so therefore its class is 0, and therefore the fundamental group upstairs is it's trivial. All right, so this is sort of like, all I'm using here is the tautological property of how this is defined. I'm just using that this is the space of all paths. So I invite you to think about this proof a few times because it's kind of obvious when kind of like it's tautological. But it's sort of probably like one of the most important things in this lecture. So please go back to this part a few times. All right, so that proves simply connectedness, and now we have to prove uniqueness. So, okay, what is the assumption? So the assumption is, okay, now we have two universal covers, by which I mean two simply connected covering spaces, called x0 tilde, q tilde, and x1 tilde with base point q1 tilde, both lying on top of xq. So this is best shown in this diagram. So we have x0, x1, and each x0 tilde, x1 tilde, and they project to x by tau 0 and tau 1. Now, what we can apply here, when you see this type of diagram, the way you should think about it, of course, immediately is like, well, I should apply the homotopy lifting property here. Right, so here we have this part, which is a covering space, and now we think of this as some random map into X. So I want to lift this up, And now, when can I lift this? Well, you have to do the check this lifting criterion with fundamental groups, which is that the image of this of at the level of fundamental groups should be contained in the image of this at the level of fundamental groups. And of course, this holds in this case because both of these fundamental groups are 0 because of the simply connected assumption. So this holds, which means that I can lift tau 0 to some map tau 0 tilde. And likewise, when I think of this as the covering space and this as the arbitrary map, then tau 1 can be lifted to a map tau 1 tilde. Awesome. Now, out of this, what I can do is I can forget, let's say, x1 tilde and just think about the composition of these two maps. So I here have a map from x0 tilde to itself, which is tau 0 tilde composed with tau 1 tilde. And now let's play the same game, but with this diagram. So what do we have here? So we have a covering space and then some arbitrary map that in this case happens to be tau 0 again. And now what we ask is, well, can we lift? Then, well, yes, of course, because the image of the fundamental group here of both is 0. So I lift tau 0, and now I observe there's, in fact, two lifts. One of them is the identity. This is the obvious lift. And the other one is this composition that we built out of this diagram. And now let's look at them. So the identity in x0 tilde, what does it do to the base point, let's say? So what it does to the base point is it preserves it, of course. And what does this do to the base point? Well, it also preserves it because we said that these maps are like base point preserving, right? Because that's the way we lifted them. We lifted them by mapping to the base point. So what that tells me is that if I have two maps that they lift the same map and they both have the same lift at one point, then they must agree by the uniqueness of the lifting property. So in fact, this thing is the identity. And so basically this is like the composition of these two is the identity, sort of arguing in the other direction, you can show that the composition of these two is the identity, which means that both of these are homeomorphisms. And that's the end of the proof. All right, let's make a tiny remark that we could have made a bit earlier, perhaps. So what did we say? So here the universal cover, right? We've said it's the source fiber over Q, and the covering map is it's a target, right? And now this is a bit tautological, but what does it? But what is the target? What is the fiber of the target? So if this is the space of the space, if these are like classes of paths starting at Q, and I take the preimage of Q by the target, then that means that, well, I'm basically fixing the source on the target to be Q. So this is exactly the fundamental group at Q. So that tells me that the fiber over Q of this covering space is canonically identified with the fundamental group of the base at Q, right? So this is completely canonical. Here I haven't made any choices somehow, except sort of, well, constructing X tilde itself. Now, after this remark, let me go basically to this, well, to this proof, and let's make a little observation. So I have to introduce some language for it. So in this previous proof we were doing, we're working with covering spaces, right? And every time in this course we've worked with a certain family of objects, we always do the same. We say, well, what are the objects? What are the natural maps between them, like the morphisms? And what are the isomorphisms, right? Like the equivalences in our world of objects we're studying. And the world we're studying right now, right, it's covering spaces with a fixed point. So pointed covering spaces, this I denote by cover sub star. And, well, what are the objects? So, okay, they're pointed covering spaces. So this is a covering space with preferred point, a map that is, yeah, covering map that is preserved space points, and a base space X with base point Q. Now, the morphisms, what should they be? And of course, they cannot just be maps in this side. They have to be maps of the whole structure. So that means that a morphism between two whole covering spaces should be like, well, a map between the base spaces, so a homeomorphism at this level. It should be a homeomorphism at the covering space level, and they both should commute with the covering space structure, so with the two covering projections. As such, a morphism in the world of pointed covering spaces is not one map, it's two maps. It's F and F tilde. However, and this is sort of similar to many of the things we've done so far, you should, I mean, in fact, for instance, we saw this, I mean, okay, maybe you should be reminded of the morphisms of groupoids, because the idea is exactly the same. So please, maybe I should make this an exercise. Try to compare this notion of morphism with the notion of morphism for a groupoid, and you'll see that it's, well, I mean, it's sort of, since this, at least for the universal cover, we defined it as a source fiber, you'll see that in fact this is like a restriction of the morphism of the fundamental groupoid. In any case, sorry, I'm rambling. So what you can check is that f, little f, can be recovered from f tilde by the following process. You start here, you take any preimage, it doesn't matter, you map it by f tilde, and then you project down. Right, so just like as in the case for groupoids, the pair f tilde is in fact recovered uniquely from f tilde as soon as you have like a nice compatibility between f tilde and the projections. All right, so this is morphisms, and what should isomorphisms be? Well, I mean, they can only be one thing, so I should require that they are invertible, and being invertible, of course, since these are topological spaces, that means that these should be homeomorphisms. All right. All right, so this side remark goes to saying that in the category of pointed covering spaces, the isomorphisms are things like this, and what we've shown here in this statement is not just that the universal cover is unique up to homeomorphism, it's in fact unique up to this precise notion of isomorphism. Okay, this is this corollary. All right, and now I think we're almost done with this video. What I'm gonna explain last is sort of the first ingredient for constructing other covering spaces, and as I said before, all of them will be built out of the universal cover by quotienting. So what I'm gonna do now is I'm gonna explain that there's like a group action in the universal cover, and by sort of quotienting parts of this action by a group, I will yield new covering spaces. So let's see exactly what the statement is. So here I have the universal cover, and what I say is the following: there is an action of the group, of the fundamental group of the base in the universal cover. This means that if you give me an element here in pi1, and you give me here a path in the fundamental groupoid, I'm able to produce another path in the fundamental groupoid. How do I do it? Well, there's only one thing we can do, right? Like these are classes of loops based at Q. These are paths, classes of paths starting at Q. So the only way I can produce another path starting at Q is just to pre-concatenate nu to gamma. And this is exactly it. All right. Yeah, here I say it's from the right, because it's a right action, right? Like I'm pre-concatenating, and which is in fact the only thing I can do. There is no left action sort of here. Right, so this is your typical group action. You've probably seen it for sets. What you should observe in this case is that this is a group action on topological spaces. So we have to, I mean, not only we have to check that this is a group action at the level of sets, we have to check that this is compatible with the topology in the universal cover. So let's check these two things. So the first observation is that at a set theoretical level, this action is well defined, and the reason is that this is just part of the product in the fundamental groupoid, right? Because, well, this is obviously part of the fundamental groupoid. These are just classes of paths, but this is also part of the fundamental groupoid, right? Like this is one of the stabilizer at Q. So that, and the way in which we are multiplying this is just the usual groupoid multiplication. So of course this is well defined. So the question is really, is this a continuous thing? And in particular, is this like, well, okay, let's see. So is this continuous? And the first observation is that at this side, on this side we have nothing to check, because pi1 as a topological space it's a set, right? It's just it has the discrete topology. So here there's no continuity to check. All we have to do is we fix some nu, And now we see how the multiplication of nu on this element acts. And we want to see that multiplying this pre-concatenating by nu for fixed nu is a continuous map of x tilde to itself. And it's immediate that it is. Why? Because the map that sends gamma to gamma pre-concatenated by nu, what does it do at the level of open sets? Well, it sends an open set of the form u vs vt gamma to an open set of the form vs vt gamma pre-concatenated by nu, sort of immediately. So that tells you basically that this is a local homeomorphism, and you can check that this is in fact a bijection as sets. So what we see, and this is what the observation says, is that this is of course these are homeomorphisms, right? For every nu I fix, I obtain a homeomorphism, and I can denote such a homeomorphism by psi nu. All right, so let me provide, so this is part of a longer story that we'll see in the next video. But let me provide a bit of more definitions. So if I have the universal cover, I will say that a homeomorphism of the universal cover that commutes with the covering map, so in case with the target map, is a deck transformation. That's the definition. And what we've just shown is that if you give me nu, an element an element of the fundamental group, then the corresponding map, the corresponding homeomorphism that I call psi nu, it's a deck transformation. All right. Out of the definition of deck transformation, what you can see is that deck transformations form a group, right? Because they can be composed, right? Like if I have a homeomorphism that commutes with tau and I have another one, I can just compose them. If I have a homomorphism that composed with tau, well, that commutes with tau, then I can take its inverse and it also commutes. So yeah, they define a group. And what we've shown basically is that the group, the fundamental group of the base, sort of gets mapped to the group of deck transformations. This is exactly what this is. And the claim is that in this case they are exactly the same for the universal cover. And why is this? What do we have to show? So we have to show that basically every deck transformation comes from an element in the fundamental group. And why is this? Well, what can a deck transformation do? A deck transformation, right? So it commutes with tau, so it's a lift. And that means that every deck transformation is completely determined by how it lifts one point, right? Once we lift one point, a lift is unique. So that tells me that it's enough to check what a deck transformation does on Q tilde, let's say. Right? And where can psi of Q tilde be mapped? Well, it can only be mapped to other classes in the fiber of Q. So that is, it can only be mapped to other elements in the fundamental group because the fiber is canonically identified with the fundamental group. And now the point is, well, in fact, all this, if I take psi nu and I apply it to Q tilde, where does it go? Well, it goes to nu itself, right? Because what does it do? It takes the path that is the constant path, it precomposes it by nu, so you end up with nu. So that tells me that for everything, for every deck transformation that could take Q tilde somewhere, I exactly have one deck transformation that does exactly that, which is the psi nu. So that proves that every deck transformation comes from I1. All right. So yeah, okay, maybe let me finish with this comment. So yeah, deck transformation is an isomorphism of non-pointed covering spaces, right? This is exactly what this diagram says. This says that this is a homeomorphism at this level that is lifting the identity in X. So yeah, okay, so in the next video we'll talk about other covering spaces. We'll see that this lemma plays a really important role, so please well, try to look at the statement, look at the proof. And maybe I don't know if there's any more words I should say to wrap up. Yeah, maybe let me say the following. So basically what you should keep in mind after all this discussion is this. So we've built the universal cover as a space of paths starting at our base point. Now the points over the base point in this universal cover, they become the elements in pi1 in a canonical way, and at the same time they become the deck transformations, right? Like the pi1 becomes like all the ways in which I can sort of produce a homomorphism of x tilde that commutes with the covering structure in a nice way. So we will see that for other covering spaces the story is quite similar, except that now, I mean, sort of how to say, for other covering spaces, we'll see that the fiber now becomes not the full pi1, of course, but pi1 quotiented by some subgroup, and this subgroup becomes exactly the fundamental group of the covering space. And we'll see that the story with the deck transformation is a bit more complicated because it has to do a bit with the normalizer of the subgroup in pi1, but that's a longer story. Okay, so let's wrap up there. Maybe try to compare these results to the covering universal covers you already know, which are like the one of S1 and the one of the wedge of two circles, and hopefully that will clarify a bit. All right, I'll see you in the next video.